Hello, this was another question requested from a student in our linear systems unit. So given the equation 3x minus 4y equals 12, we want to write a second equation to form a linear system which A has infinite many solutions, B has no solutions, and C has one solution. So conceptually what we want to remember here is that, and we'll just color code these as we write them out. So let's say this is A here. We'll do A in black, we'll do B in blue, and we'll do C in green. So key thing to remember with infinite many solutions is if we set up our two equations, what we end up with is we'll end up with something along the lines of 0x equals 0, or if we're solving for y, we'll get 0y equals 0. And the reason why this indicates infinite number of solutions is because what it says is that I can put any x that I want into here and it's going to work. So that means every value of x is valid. Likewise with y. So this case occurs when the lines are the same. So therefore, if equation 1 is what we have is 3x minus 4y equals 12, what I need to find is a second equation that is the same line. So if I really wanted to, I could say another possibility is 3x minus 4y equals 12. So there is a second line that has infinite many solutions because they're the same. However, if I wanted to be a little bit more tricky about it, what I might do is multiply both sides of the equation by some constant. So if we multiply the left side and the right side by the same thing, there's no effect on the actual line itself. So let's take both sides of our original equation and multiply it by 2. So we're going to say 6x minus 8y is equal to 24. So that's equation 1, and there's our equation 2. Though these lines look different initially, they are actually the exact same line. It's just the second one is the first one times 2. If we tried to solve this algebraically, what we might do is we might take the first equation and multiply it by 2. So we're going to say times 2. So we'll get 6x minus 4y equals 24. And then equation 2 is going to remain 6x minus 4y equals 24. And then if I subtract these two equations, I end up with 0x plus 0y equals 0. And there is my indicator. Since x is times 0 and y times 0, any value of x here makes sense. So again, the key thing is if they are two lines of infinite many solutions, the lines must be the same. Okay, part B. So now we want to deal with a situation where there's no solution. So in class we talked about this, and what we said was that, let's just draw a quick sketch. If they have no solution, what it means is that they're parallel, but they have a different y-intercept. So if two lines are parallel, that means they're never going to touch. But it's very important that you include parallel and distinct. This part distinct is important because notice in A, if two lines are the same line, they are parallel as well. So you need to say parallel and distinct. Algebraically, what we'll end up with is we'll end up with something along the lines of 0x equals some value, or we're going to get 0y equals some value. Oh, pardon me. Because if we look at this, 0 times anything is 0, therefore there's no value that x can have that was going to result in some number over here other than 0. So again, our equation 1 here is 3x minus 4y equals 12. And what I want to do is I want to set up a situation where when I add these two equations or subtract these two equations, I end up with a constant on one side, but 0x and 0y on the other side. So let's actually just set the same coefficients for x and y. And over here, let's actually put a value that is that is different than 12. So let's put, I don't know, 13. Or let's put 11, in fact. So what I've done now is I've set up a situation that if I try and solve this system using elimination, I'm going to subtract the two equations. I'm going to get 0x plus 0y, and 12 minus 11 is 1. And so since we get this case of 0x, 0y equals 1, we know that there is no value that satisfies zero x plus 0y equals 1. So that can never happen. So therefore, these two lines have no solution. They are parallel and distinct. Part C is we want one solution. So that is a situation where we can work out and solve the two equations to get some value. And this is probably your easiest case because there's lots of possible answers to this. So when we have one solution, that means when the lines touch. So a couple ways I could do this. One way might be, let's take our equation 3x minus 4y equals 12. And I'm just going to take a second and rearrange this. So we get minus 4y equals minus 3x plus 12. We're going to divide both sides by minus 4, so y is equal to 3 over 4x minus 3. So now there's equation 1, that's the same equation. So I can just come up with another equation as long as these don't cancel out and disappear, we're okay. So let's make our second equation. It could be something like y equals, I don't know, negative 1 over 2 x. Actually, let's keep it over 4, and I'll see why in a second. Negative 1 over 4x plus 6. Okay, so there's my second equation. I can show that these two have a solution now by solving it. So since y is already isolated in both cases, I can say 3 over 4x minus 3 is equal to negative 1 over 4x plus 6. Let's multiply both sides by 4, so we get 3x minus 12 is equal to minus x plus 24. So we're going to get 3x plus x is equal to 24 plus 12. So we get 4x is equal to 24 plus 12 is 36. And so we divide both sides by 4, so we get x is equal to 9. Therefore, if x is equal to 9, we can sub this 9 back in. Y is equal to negative 1 over 4 times 9 plus 6. And of course, I can get my calculator out and work that out if I need to. So this is a nice problem because it highlights the three cases we could run into with systems of equations, and you need to know these. It might have an infinite number of solutions, so infinitely many solutions, meaning they're just the same line. They might have no solutions, meaning that the lines are parallel and distinct. Don't forget that word distinct. Or one solution. And one solution is just where you work out your system and you end up getting an actual answer. I hope that helped.